For this problem, we're given a circular loop of wire with a radius r that exists in the plane of a page. And we're also given that there's a magnetic field throughout the region of the loop that's directed out of the page. And we are also given that the magnetic field is described from t equals 0 as b of t equals at cubed plus bt squared, a and b being positive constants. And so I wrote out the equation that we were given that describes the magnetic field, and I graphed this on my calculator. And as long as a and b are positive constants, which they are, the graph looks approximately like this. And so for a, we're asked to describe the direction of the induced current. And since it starts from t equals 0, you can cut off the left part of this graph, the left half, and start from here. And as you can see, as t increases, b of t, the magnetic field, just keeps increasing constantly. And so we can say, and since what that means is the magnetic field directed out of the page constantly keeps increasing. And so when this happens, the induced current, it tends to want to even things out. So since there is a great amount of current going out of the page, a great amount of magnetic field going out of the page, the induced current will be going into the page. So, and it'll be, since it's always increasing, the induced current will always be increasing into the page to kind of counteract the magnetic field. And so for B, we are asked to derive an expression for the amount of induced EMF in the wire. And so I started off using Faraday's law of induction, where in here I showed, I guess, the magnetic flux phi equals the magnetic field equals the integral and of a closed surface of the magnetic field times dA, the area, derivative of the area. And I also used another almost corollary of Faraday's law of induction, that the EMF equals the rate of change of magnetic flux right here. And so I just kind of combined these two equations to some extent, and I plugged in the magnetic field times dA into, so phi, or the magnetic flux, into this equation over here to the right. And so that put me with the EMF equals negative derivative of this, the integral of b dot dA over dt. And so that simplifies, after all that, simplifies down to negative dB over dt times A times cosine of theta for the dot product. But since they are parallel, since the magnetic field and the area are parallel, the cosine of theta cancels out to being equal to 1. And so you can get rid of that. And so then after some more simplification and some substitution, substituting the original equation that we were given for that describes the magnetic field into the dB, we can say that the EMF equals negative derivative of AT cubed plus BT squared all over dt times A, times the area. And since the area is pi r squared, we can just plug that in for A, and we can say that the EMF equals 3AT squared plus 2BT, that's the derivative of this over here, times the area pi r squared.